Hello. Welcome to the discussion of multimodal AI. Imagine pointing your phone's camera at a dish you've never seen before and instantly getting a detailed description and recipe for it. Or consider a car that not only sees the road through cameras, but also hears sirens and reads traffic signs to make driving decisions. Thanks to multimodal AI, these scenarios become reality. Now, artificial intelligence can understand and generate multiple types of data, modalities like text, images, audio, and even video. This video is a brief introduction to multimodal AI, what it is, why it matters, how it works, real-world applications, key technologies like GPT, Clip, and Whisper, underlying principles, current challenges, and future possibilities. Multimodal AI refers to AI systems that can simultaneously process and interpret data from various sources, such as natural language, visuals, and sounds, rather than being limited to a single input type. Traditional AI models are unimodal. They typically focus on one modality at a time. For example, a speech recognizer that only takes audio, or a caption generator that only takes images. In contrast, a multimodal system can take combined inputs, like an image and a question about the image, and produce combined outputs, like a textual answer, possibly with an image. This allows the AI to develop a more holistic understanding of information, akin to how humans use multiple senses, sight, hearing, touch, etc., to perceive the world. Why is this important? Because the world is multimodal by nature. We rarely rely on just one sense or data type to learn or make decisions. For example, when you watch a lecturer, you're listening to words, seeing gestures, slides, and maybe reading accompanying text. Similarly, an AI that can combine modalities can understand context and nuances better. Multimodal AI is considered one of the most promising frontiers in AI's evolution, a key step toward more general and human-like intelligence. After text-only generative AI, like the original ChatGPT, took the world by storm, researchers quickly turned to multimodal learning as what's next, enabling models that see and hear in addition to read. In fact, the current version of OpenAI's GPT is multimodal, meaning it accepts both text and image inputs and outputs text. Such advances hint that combining senses could bring AI systems closer to human-level performance on a wider range of tasks. Multimodal AI also makes AI more practical, allowing for more natural interactions, such as voice and vision together, and unlocking applications that were impossible for single-modality AI. At its core, multimodal AI is about fusing information from different sources into a cohesive understanding. Each data modality, text, images, audio, video, etc., has very different characteristics. For instance, text is sequential and symbolic, images are spatial and pixel-based, audio is time series, video is temporal visual data. A multimodal system typically processes each modality with specialized techniques and then combines the extracted information. Let's walk through the process step by step. The first step is feature extraction. In this step, the AI model extracts features from each input modality separately, such as using computer vision to extract visual features from an image and natural language processing to extract semantic meaning from a text passage. In practice, this often means using separate neural network components, such as a visual encoder, like a convolutional network or vision transformer, to encode images, and a language encoder, transformer, to encode text. Each encoder turns its input into a numerical representation, a list of numbers called an embedding or feature vector, capturing the important patterns. The next step is data fusion. In this step, the model integrates these representations from multiple modalities into a joint understanding. There are different strategies for this fusion. An early fusion might combine raw data or low-level features, for instance, combining image pixels and text characters in one big model input, whereas late fusion combines high-level features after each modality is processed separately. Many state-of-the-art models use a form of mid-fusion using a unified architecture, like a transformer, that can attend to text and visual features together. The goal is to have the model learn associations between modalities. For example, linking the word cat with the visual features of cats, or matching the sound of barking with images of dogs. By fusing the data, the model can understand context that is only apparent when modalities are combined. For instance, interpreting a movie scene by combining what's said with what's happening in the video. One intuitive way to think about integration is teaching the AI a shared language for different data types. For example, OpenAI's CLIP model trains two encoders, one for text and one for images, so that they produce vectors in the same space for semantically similar inputs. If you give CLIP the caption, "Two dogs running across a frosty field," and an image of two dogs running in a snowy field, it will generate two vectors that are very close together, highly similar in that shared space. Multimodal models often use cross-modal attention mechanisms, essentially allowing the model to cross-reference one modality with another. For instance, a model answering questions about an image might attend to the relevant part of the image when certain words in the question are processed. "Where is the cat?" prompts the model to focus on image regions likely containing a cat. Thanks to these techniques, multimodal AI can interpret inputs in a way that a single modality model cannot, leading to richer and more accurate outputs. Multimodal AI is not just a research curiosity. It's powering an array of applications across different industries. In the following, we will discuss some key areas transformed by multimodal AI. In healthcare, multimodal AI helps doctors and researchers make sense of the full spectrum of patient data. Consider a scenario involving a difficult diagnosis. A doctor has access to a patient's electronic health records, text data, lab test results, structured data, medical images like X-rays or MRIs, visual data, perhaps even genomic sequences or sensor data from wearables. A multimodal AI can ingest all of this. For example, an AI assistant could read a patient's symptoms and history, examine their chest X-ray, and listen to an audio recording of the patient's cough, then combine these inputs to suggest likely conditions. This is not far-fetched. Multimodal models in medicine are already being developed to process records, imaging, and even genomic data together. By seeing the bigger picture, such systems might detect patterns that a specialist could miss in isolated data streams, potentially leading to earlier and more accurate diagnoses. Multimodal AI is making education more interactive and personalized. Traditional e-learning might involve reading text and looking at images, but modern AI tutors can incorporate text, visuals, and audio for a richer experience. For example, a language learning app like Duolingo uses multimodal AI to great effect. Duolingo combines text, audio, and images in its lessons and uses AI to adjust to the learner's level. The multimodal feedback loop keeps students more engaged than text-only drills. Beyond language learning, imagine AI tutors for other subjects, a biology app where you can sketch a cell and the AI labels your drawing while explaining in audio, or a history tutor where you upload a historical painting and the AI narrates the event depicted and answers your questions. By integrating video, interactive diagrams, voice, and text, education AI systems can cater to different learning styles: visual, auditory, kinesthetic, essentially personalizing education. Studies show that such multimedia learning can improve understanding and retention, as the AI can present information in the mode the student finds most intuitive. This also helps keep students with different preferences or disabilities on the same page. For instance, Deaf students can benefit from visual and text materials, while blind students benefit from audio descriptions. The entertainment industry is embracing multimodal AI for content creation and immersive experiences. Generative AI models can now create art, music, and even video from prompts, and multimodal models often drive these capabilities. Multimodal AI is also creating audio-visual experiences. AI music generators can produce background scores based on the mood described in text. AI models, such as Sora, can also generate video clips from text prompts. In filmmaking, AI can help with tasks like automatically storyboarding scenes. A director could feed the script and get a sequence of AI-generated rough images depicting each scene. For social media and content creators, multimodal AI enables features like auto-captioning videos, transforming video content into text summaries, or vice versa. Video platforms already use AI to recommend content by analyzing both the video frames and the transcript to understand context. In gaming and VR, multimodal AI might power NPCs, non-player characters, that respond to your spoken commands and gestures, or dynamically generate new game content, landscapes, puzzles, etc., from descriptions. The blending of language, vision, and sound is key to making these virtual worlds more realistic and interactive. As creative AIs improve, we're likely to see entirely new forms of entertainment co-created by humans and AI, from AI-augmented reality games to personalized interactive stories that unfold differently for each user based on their reactions, such as facial expressions, choices, etc. One of the most heartwarming uses of multimodal AI is in making technology more accessible to people with disabilities. Because it can translate information from one modality to another, multimodal AI serves as a bridge for people who lack one modality. A prime example is using AI to help blind or visually impaired individuals see the world through descriptions. Google and Microsoft have developed AI systems that generate image descriptions, captions, automatically for use in screen readers. Similarly, multimodal AI aids people who are deaf or hard of hearing by providing automatic speech-to-text transcription for live conversations, phone calls, or videos. Models like OpenAI's Whisper are remarkably good at this. Whisper is a speech recognition model trained on 680,000 hours of multilingual audio, making it very robust to different accents and background noise. However, there is still room for improvement in accuracy. For example, in a YouTube video about quantum computing, sometimes the term qubit, Q-U-B-I-T, is mistakenly transcribed as qubit, C-U-B-I-T. Robots that operate in the real world must inherently be multimodal. An autonomous car is a great example. It uses cameras, vision, LiDAR, radar, depth sensors, GPS, numeric data, and sometimes microphones, audio, all together to understand its environment. A self-driving car's AI might fuse input from a front camera, seeing a red object ahead, a microphone, hearing a siren, and a radar sensor, measuring distance. Individually, each signal might be ambiguous. Together, the AI concludes there's an ambulance approaching and decides to pull over. Multimodal AI is crucial in such scenarios for safe and intelligent decision-making. Tesla's autopilot, Waymo's vehicles, and other autonomous systems use neural networks that take in images from multiple cameras and other sensor readings to output driving actions. They have to detect and cross-verify objects. Is that blob a pedestrian or a tree shadow? Using all available data. Any hallucination or misalignment, such as vision misinterpreting something, could cause errors, so the fusion is done with care and often with redundancy for safety. Beyond cars, in general robotics and AI assistance, multimodal learning is enabling more versatile robots. Consider a home assistant robot. It should recognize your voice command. Bring me the red book from the shelf. Use vision to identify the red book and navigate. Maybe use touch sensors to grasp it and then bring it to you. Researchers are building vision language action models for robots that connect natural language understanding with visual scene understanding and physical action. For instance, Google's Palm E is an embodied multimodal model that can interpret commands in words and carry them out in a simulated robot environment, combining language with camera input. Several cutting-edge AI models and systems have pioneered the multimodal approach. These include OpenAI's GPT and Google Gemini. In the open source community, models like BLIP, VisualBERT, and Perceiver.io explore different ways to architect multimodal systems. The common trend is that these are all foundation models, large pre-trained models on massive data that can be adapted to many tasks, much like GPT-3 was for text, except now they see and/or hear as well. While each model has its own architecture details, there are some high-level principles behind modern multimodal AI worth understanding. The key idea is that we want the model to learn joint representations of different modalities. In other words, a way to represent, say, an image and a caption such that the model can easily correlate the two. In the following, we will go over a few principles. The first principle entails embeddings and common representations. An embedding is a numerical representation of data. Multimodal models often bring different data types into a common embedding space. Imagine a huge room where every concept is a point in space. A text encoder might place the word dog at some coordinate. We want a picture of a dog, when fed through an image encoder, to end up in the same neighborhood as that word. By training on lots of image caption pairs, the model adjusts the encoders to make this happen. Once aligned, this space is a powerful tool. To find the caption for an image, you just find which text embedding is nearest. To generate an image from text, you can start from the text's embedding and work backward to pixels. That's essentially what generative models do. CLIP's success showed that contrastive learning is a robust way to create such a shared space. The second key component is the transformer architecture for all modalities. Transformers were originally invented for language, but they've become a unifying architecture for multimodal AI. A transformer can process a sequence of tokens, which could be words, or patches of an image, or frames of a video, or spectrogram pieces of audio. In fact, vision transformers split an image into a grid of patches and treat each patch like a word to encode it. This means in many cases, images, text, and audio can all be handled with similar model designs, just different input preprocessing. Many multimodal models employ multiple training tasks, meaning multitask or multitask learning. For example, a single model might be trained to do image captioning, text-to-image generation, and image-text matching. By doing so, it gains flexibility. Whisper's training, for instance, included both transcription and translation tasks in many languages, which improved its overall capability. Another core principle is alignment and co-learning, in which the model should learn from cross-modal signals. If an AI sees a silent video of someone speaking and also gets the transcript, it can learn to lip read by aligning the visual mouth movements with the spoken words. If it reads a book and also sees illustrations in the book, it learns to connect narrative descriptions to imagery. This co-learning often requires curated paired data, like image caption datasets or video with subtitles. One challenge is that such paired datasets are less abundant than single modal data. There's vastly more pure text on the internet than there are images with good captions, for instance. Researchers thus use a mix of approaches, using as much paired data as available, and sometimes using unpaired data with clever proxy tasks, like training a video model with narration by treating the narration as text paired with video frames. Although they're loosely aligned, it's still helpful. For producing outputs in multiple modalities, models often have separate decoders and generative components. A single system could have one branch that can generate text and another that can generate images. For example, OpenAI ChatGPT is specific to language processing, whereas DALL-E aims to image generation. Nonetheless, today these functionalities are integrated. Now you can use ChatGPT to perform multimedia tasking. To be specific in ChatGPT, you don't have to select Create Images. Rather, in the Ask Anything box, you can simply enter a prompt like, please create an image of a small town in Italy, output it in the landscape dimension, 10 by 8, and the image would be produced accordingly. Despite all the excitement, today's multimodal AI systems have several important limitations and challenges. It's crucial to understand these, both to set realistic expectations and to drive future improvements. Multimodal models are data hungry. They often require enormous data sets that include multiple modalities together. Additionally, each modality can introduce noise. An image might be blurry, audio might have background chatter, text might have typos or slang. The model has to learn to be robust to all these, which often means even more data are needed. Combining modalities is not a trivial task. Different data types have different statistical properties, and the model's hyperparameters, like learning rates, might need tuning for each. The complexity of architectures that handle multiple inputs is higher, meaning more things can go wrong. Further, getting different modalities to agree inside the model is tricky. Sometimes the model might generate outputs that are inconsistent with one of the inputs, a phenomenon often called hallucination in multimodal models. In conclusion, multimodal AI is an exciting leap toward AI that understands the world more like we do. Through a rich tapestry of inputs, it brings huge potential benefits, more intuitive AI interactions, systems that can solve complex real-world problems by seeing, hearing context, and assistive technologies that can truly augment human capabilities. It also brings challenges that we must carefully navigate, from technical hurdles to ethical dilemmas. The coming years will likely see multimodal AI permeate everything from our search engines to our kitchens to our classrooms. By understanding the concept of multimodal AI now, you'll be prepared to leverage this technology. Thanks for watching. I hope this introduction sparked your passion for the endless possibilities of multimodal AI. This is only the beginning. The sky is the limit. How might you use multimodal AI to boost your productivity? I'd love to hear your thoughts.